All right, well, I'll begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for this class and just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So we have begun our discussion of vector calculus. I will remind you guys that the first order of business here is to understand differentiation. And admittedly, these derivatives are a little bit unmotivated. The gradient of a function, this we've talked about before, right? And the formula there, I equals 1 to 3. We'll stick with 3 dimensions here today. Partial f, partial xi, x hat I. And that was the formula for the gradient. The divergence of a vector field, let's say f, is likewise the sum I equals 1 to 3 of partial f sub I, partial x sub I. So it's just the sum of the derivatives of the component functions, each with respect to the component in question, right? So like x with the x derivative, the y with the y derivative, the z with the z derivative. Sum of those is the divergence of the vector field. This is, again, a scalar function, really. The divergence of a vector field is a function. The gradient of a function is a vector field, right? And finally, last but most perhaps challengingly, the curl of a vector field is equal to the sum over ij and k of epsilon ij k partial f sub j partial x sub I x hat k. So the curl of a vector field is once more a vector field. And formally speaking, it kind of is taking on a life of itself. Some people like to talk about the vector in this sense, like x hat partial partial x plus y hat partial partial y plus z hat partial partial z. And I don't engage in that too much in terms of like a guiding principle, but that pattern is there to see. Yeah.
Sorry, isn't the gradient already a vector?
The gradient what?
Isn't it already a vector?
Well, the gradient, are we talking about the gradient of a function?
I'm not sure. I just whatever the vector is.
So like up here, the gradient of a function, right? That is a vector field. But this down here, we've never talked about. On its lonesome, I mean, this is a vector of operators. Sometimes this is called the del operator. And in some sense, if you take the dot product, see this? If you elevate, I don't write vectors on nabla because it's just kind of annoying. But if you were to write a vector on a nabla, you kind of see there's a preservation of vectorness here, right? Like this makes that a vector. The dot product of two vectors is a scalar. The cross product of two vectors is a vector, right? So there's a certain logic in thinking of this as a vector, but I don't want to do that because it's really just a mnemonic. And anyway, but that thought is present in science and engineering literature, so I thought I should mention it. All right, so the question I want to ask today is, well, first of all, we'll do some more calculations, right? But first I'd like to prove the properties of these, right? We've already done the properties of the gradient, right? What are those? Given f and g functions, right? We know that the gradient of f plus g is gradient f plus gradient g, right? We worked this out before. We know that the gradient of a product of two functions is what? The gradient of the first times the second plus the first times the gradient of the second, right? That was another property we had for gradients. We even, in the homework, I think I gave you guys, oh wait a minute, I may be thinking of another class. There's a quotient rule for gradients too if you want, all right? But I never use that, so I'm not going to write it down. More importantly is if h is like a function from the reals to the reals, right? And we form let's see here. So H composed with F would make sense, right? Because like that'd be like R3 to R again, right? So this, like the first composition is F, and then the second H works last, right? So like specifically H of F of, well, there's nothing more to write. Okay, anyway, so the gradient of H of F of X, Y, Z, right? That one, right? How'd that go? Well, that was basically, we could write it this way, dH dF times nabla F. Excuse me, times nabla F. In other words, more explicitly, H prime of F of X, Y, Z, right, times the gradient of F. Now that's the chain rule for the gradient. That's perhaps the most useful one in some sense. Here, like as an application of this, you remember if we look at F of X, Y, Z equals to the square root of X squared plus Y squared plus Z squared, for example, right? Then what is partial F partial X equal to? We've got what? We got 1 over oh, my bad. That's not what I wanted to do. Sorry, erase the square root. Erase the square root. Sorry, now it's easy, right? Partial F partial X is what? 2x, right? Partial F partial Y. 2y, partial F partial Z. 2z, right? So what if we look at H of U equal to the square root of U, right? Then you know H prime of U is 1 over 2 times the square root of U, right? Yeah? So what's the gradient of the square root of X squared plus Y squared plus Z squared, yeah? I can look at this as the gradient of H of F of X, Y, Z, right? And so what that gives me is 1 over 2 times the square root of X squared plus Y squared plus Z squared times the gradient of F, which is what? 2x, 2y, 2z, because we just worked that out, yeah? And so if I do this, if I think clearly, I can use the quotient rule to avoid a bunch of repeated differentiations of the same function, right? Like if I do this, I differentiate the square root function once, and that's it, right? Whereas if I was to just put the square root on the function to start with and just differentiate like I was doing, I would end up having to differentiate the square root function 3 times. I mean, it's kind of a silly point, but there it is. It's the point. Now, can you guys take this calculation that I'm doing here and kind of, like, let's see something from it? What does this calculation show in the blue, really? Another notation for this would be like what? The gradient of rho is what? X, Y, Z divided by the square root of X squared plus Y squared plus Z squared, right? Canceling the 2 out. In other words, you've got X over rho, Y over rho, Z over rho. Of course, that was also rho hat, right? So we've done this before. This is a brief review. So, all right. Just a reminder, we already know properties of gradient, right? Let us move on. Oh, so also, of course, we can pull constants out, right? If I have a constant like here, that pulls out to here, right? No big deal. Now let's talk about properties of the divergence. So in order to do that, let's consider a vector field F and a scalar function G, all right? And also, we'll also consider a vector field G, all right? So first of all, number one, the divergence of F plus G, guess what? It's the sum of the divergence of F and the divergence of G. Number two, what if you've got a constant times your vector field? How do you think that goes? Can we pull a constant out of the divergence? Yes, we can. So constant times the divergence of F, all right. Number three, what if we have the divergence of, now I can't multiply functions, right? Can I can't multiply functions, I can multiply, excuse me. Can I multiply vector fields? No, that's not right. I mean, we could take the dot product of them. We could take the cross product of them. We could do that. But let's see here. But the most simple thing to do is take the G times F, right? The scalar multiple of the scalar function G times the vector field F, right? What do you think? Is there a product rule here? Well, yes, there is. What do you think it is? Yep.
Not with the times.
Now you say times. What do you mean by that?
Not with the dot, the vector field, plus what's it called?
The divergence,
The
right?
divergence.
Divergence, yeah. So you know that the divergence is a scalar, right? So it almost forces us to write this formula, right? Now, but there's something else we could do in terms of multiplying functions. What would that be? Can we take the two vector fields and make another vector field? We could add them. I did that already. What else could we do? How can you take two vectors and make another vector? Cross product, yeah. So we could do this. And I'm gonna leave a blank here to fill in. We're gonna work that out because that's not obvious. All right. So let's look at the proof of these. So I'll do 1 and 2 together. So we take the divergence of, let's say, C times F plus G is equal to the sum, I equals 1 to 3, of, let's see here, C, oops, my bad, partial xi, right, of the ith component. What's the ith component of CF plus G? It is C times F sub I plus G sub I, right? The ith component of CF plus G is just CF sub I plus G sub I, right? That's basically the definition of scalar multiplication and vector addition. And then, all right, we can pull a constant outside the derivative, and we can pull it outside the sum. So I get C times the sum, I equals 1 to 3 of partial F sub I, partial X sub I, plus the sum I equals 1 to 3 of partial G sub I, partial X sub I. Now, I'm sorry, I did do two things at once here. On the one hand, I first of all used that the partial derivative has what? It is itself allowing us to pull out constants, right? And break up across addition, right? Because the partial derivative is what we call a linear operator. It's a linear operator. And then the other property I used was just the arithmetic of finite sums. The finite sum of a sum is the sum of the finite sums. And you can pull a constant out of a finite sum as well. And what do we have? Well, this is C times the divergence of F plus the divergence of G, and there you go. If you put C equals to 1, you get 1. And if you put G equals to 0, you get 2, right? So it's a twofer. We proved 1 and 2 at the same time. All right? How do we prove 2? Let's do it. Rather 3. I already did 2. Here we go. So we got the divergence of G times F. And so that's the sum. I equals 1 to 3 of partial xi of G times F sub I, right? Since if we look at G times the vector field F, calculate the ith component of that, that's exactly equal to G times the ith component. That's how we scalar multiply rather. Now G times F sub I, that's a product of two functions of x, y, and z, right? So we have a product rule for partial derivatives. And so that gives me the sum I equals 1 to 3 of partial G partial xi F sub I plus G times partial F sub I partial x sub I. That right here, that's just, product rule. For the partial derivative. Now we need to recognize what we're looking at. So what is partial G partial xi actually equal to in terms of the gradient of G? That's nothing more than nabla G, the ith component of it, times F sub I. And I'll write the other sum over here, sum. I'll pull the G out because it doesn't depend on I. Partial F sub I, partial x sub I. Now at this point, I need to remind you guys, if we have A dot B, in terms of summation notation, the formula for the dot product looks like this. I equals 1 to 3 of A sub I, B sub I. That's the formula for the dot product in the summation notation. Now, in contrast, the formula for the cross product, it's more fun. It's the sum over ijk, epsilon ijk, A sub I, B sub j, x hat k. Now, we don't need that one just yet, do we? Because there's no cross products in the proof of 3. I just put them out there. Just want to put it out there. So you guys tell me, what are we looking at? This is nothing more than the divergence of G dot F, right? And this right here is clearly G times the divergence of F, which is what we set out to prove. All right? Now, yeah?
Why doesn't Fi have a vector thing over it?
Because it's the ith component. So like F vector, right, is equal to the sum I equals 1 to 3 of F sub I, x sub I hat, right? F sub I is scalar. It's a scalar. If we're thinking about it as a function, it's a function from R3 to R. If we're thinking about a specific fixed vector, it's literally a number. F sub I is literally a number.
Okay.
If we fix the point, it's a number.
And so when we add up, okay, so that is the dot product.
Yeah, that's exactly the dot product of, the gradient of g with f. Now 4 is a little bit more troublesome, right? How are we going to calculate 4? Let's work it out. So we're looking at the divergence of the cross product of f and g. So that is, by definition, the sum. I equals 1 to 3. Come on. Actually, if you don't mind, I'm going to use k equals 1 to 3. Let me mix it up a bit here. Partial x sub k of the kth component of the cross product of f and g. Yeah. Now, look, can you guys tell me what the kth component? Look at this right here, right? Is there a question or no? So if we have the cross product of a and b, you can read from that formula what was the kth component. Let me write it down for you. So it is, we just need to strip off the coefficient of x hat sub k in my formula for the cross product. So like, what we're looking at then is the sum over I and j, oh come on, I and j equals 1 to 3 of epsilon I, j, k, f sub I, g sub j. Notice the lack, no x hat k here, all right? I'm just talking, that is the kth component of the cross product. All right? So then the epsilon ijk, remember, so the way epsilon works, if you guys remember, epsilon 1, 2, 3 is epsilon 2, 3, 1, is epsilon 3, 1, 2 is 1, epsilon 3, 2, 1 is epsilon 2, 1, 3, is epsilon 1, 3, 2 is minus 1, and else epsilon ijk is equal to 0, right? But the larger point is, for any choice, any distinct triple of the 27 possible distinct triples that you can take from the indices I, j, and k ranging from 1 to 3, all of those, either 0 or 1, they're all constants, right? Which means we can pull them outside the derivative without consequence, yeah? So this is the same as the sum, and I can also pull the summation out because property of the derivative. So I've got the sum over I, j, and k of epsilon I, j, k partial xk of f sub I times g sub j. That's what I have. But now we have the derivative of a product, right? So we can do the product rule. I'm going to do it up here. Otherwise, I'm going to run out of board space. So the sum over I, j, k, epsilon I, j, k. And then what we got is we've got partial f sub I with respect to the kth coordinate differentiated times g sub j plus f sub I partial g sub j partial x sub k, like that. Now I got to be careful. This one's good all right, so like I can, this right here, all right. Let's see here. All right. So I can rewrite that as, I'm going to do the sum over j out. So you can reorder the sums however you like. I'm going to do sum over j equals 1 to 3 the sum over I and k equals 1 to 3 of epsilon I, j, k, partial f sub I, partial x sub k, that times g sub j. And over here, I'm going to do the sum over I out first. Sum I equals 1 to 3 of the sum j and k equals 1 to 3 of epsilon I, j. I should have pulled the f sub I out here. Sorry, guys. I can pull the f sub I out of the sum over j and k because it's constant in j and k. So I've got epsilon ijk partial gj partial xk. You notice that this derivation is like, I don't know if you can see the wheels turning in my brain or not, but like I felt like my processor went from like 20% to 90% with this calculation all of a sudden. I actually have to think a lot more about what I'm doing, otherwise I'm going to get it wrong. So listen, what I'm trying to do is I'm trying to reformulate these as dot products. I know they must work out to dot products. And so like this j out here, this is going to be like, this is the jth component. That's like the jth component of something, but it's not quite the right pattern yet, you see, because look, if you look at the pattern for the definition of the curl, which I'll write here, the curl of f was what? If I write the jth component of it, it would look like this. It would be the sum over, I guess I and k is my current notation, of epsilon I, k, j, and then we do partial f sub k partial x sub I. That's the pattern I need to pick up the jth component of the curl there, but you notice that the indices are not in the right order. See this? ijk, what I need is ikj. So what does that mean? Yeah, I mean, what are the properties of the epsilon symbol is if we flip any pair of indices, we get a minus. This is like the fundamental thing about it. Any flip of a pair gives you a minus of what you started with. That's how it's constructed. It's the completely anti-symmetric symbol. And so what that means then is this is minus the sum j equals 1 to 3 of the sum I and k epsilon I kj partial f. Oh, come on. Guys, you got to stop me before I go further. Look, I've got the I and the k in a different way here. So you guys got to stop me. That's not, the pattern's wrong. Hold the phone. All right. Think about this some more. All right. So I didn't want to write it like this. I want to write sum over, this would be I. All right. Let me make it look like that. I'm trying to match with this. Okay, I got an I, I got a k here. If I do that, I have to put the k first and the I second, because the derivative is matching the k, and then the ith component we differentiate. That gives us the jth component of the curl. All right, now I've got it in order. So what's the deal? To get from ijk to kij, what do I have to do? So epsilon, I'll work it out here. Epsilon kij is equal to minus epsilon ikj. is equal to minus epsilon I j k, right? So actually, there is no negative because it takes two swaps for us to get to I equals 1 to 3. The sum over I and k equals 1 to 3 of epsilon kij is what I wanted. Partial f sub I, partial x sub k. All right. All of that times g sub j. Now over here, I'm pretty sure there's a minus on this one. So this is the sum I equals 1 to 3 of f sub I. I hope I'm not doing your homework right now. Sum jk equals 1 to 3. I feel like I might be. This feels homeworky. I definitely need the I in the last spot here. And, golly, this chair's in the way. Let's see here. So I need the k to come first, and then the j to come second in order to make this the curl that I'm trying to. I can't change the j and the k on the derivatives, right? Those came from the original expression, but I can flip the order of this round. Now, notice that here, to get from ijk to kji, I did what? I just swapped the outer pair, right? So that's why there's a minus. It's just one transposition of indices to get from here to here. All right, so now we're done, almost, because what we have is the sum over j equals 1 to 3. That is the curl of f, the jth component, times g sub j. And then over here, minus the sum I equals 1 to 3 of f sub I times the curl of g, the ith component of that. And what is that? So we've got the curl of f dotted with g minus f dotted with the curl of g. Whew. Golly. All right, that took me a minute. So we've got curl of f dotted with g minus f dot the curl of g. Any questions? These are the, I would say, elementary properties. The last one wasn't so elementary, was it? But these are the basic properties of the divergence, let's say. Let us now turn to the curl and see if we can find corresponding properties for the curl, right? I'm trying to think if there's anything else I want to say at the moment. There's one that I've left out of this discussion. If you think back to the gradient, what else could we have done for two vector fields now? How can you create a scalar function? How can you create a scalar function from two vector fields? What's that? Dot product. What do you guys think the gradient of the dot product of two vector fields is? So it turns out that the answer is well here. See number 4? You see number 4? Number 4? See number 4? You see number 4? See number 4?
That's so fun.
See number 4? That's the dot product. That's the gradient of the dot product of two vector fields. This is Introduction to Electrodynamics by Griffiths. This is a junior level electromagnetism test class textbook. And ooh, it's got a phone number. I probably shouldn't put that on camera. I don't think I have that phone number anymore, but I think my mom does. I better not. But anyway, you can look after class on the way out if you want. But or I'll tell you, I'll try to scan it and post it in announcements so you guys can see. It's horrible. It's got 4 terms, and it has things I don't even have names for. And you might think, does that even matter? Yes, everything matters eventually, is what I've learned teaching out of that textbook this semester. Every single one of these identities is used with deep physical meaning. Actually, yeah. What's that? Memorize. No, you need to learn how to derive them. So, what if we have curl? So instead of dot, cross, cross, cross. Ooh. Oh. That seems bad. The curl, the cross product of the cross product. I have a bad feeling about this one. All right, I have a bad feeling about that one. As hard as this was, I think this is going to be worse. So I'm relatively sure that you guys can figure out how to do numbers 1 and 2 here. What do you think? What do you think the story is? What, it's just going to be the same thing, right? And we should be able to prove these pretty easily, I think. Yeah. What goes for number 4 here? We'll figure it out. Number 5, I'm gonna say probably it's this, but I'm gonna put a question mark right here because I'm not sure about the sign there. I have a plus or minus. I hedge my bets here. All right, so the proof of 1 and 2 makes a decent test question. All right, and so here's the way that goes. If we take the curl of CF plus G, then we've got the sum I, J, and K of epsilon I, J, K partial x sub I of the jth component of this, which is CFJ plus GJ. All right, and so that is the sum over I, J, and K, epsilon I, J, K of a, well, let me just go ahead and do a little bit more on here. So that's partial Fj, partial Xi, and then of course you've got plus another sum over I, J, and K, epsilon I, J, K. I'm doing 2 steps at once here. I hope you guys can forgive me. All right. The first step is just linearity of the derivative. The second step is, properties of the finite sum. So what do you got? Well, this is nothing more than, oh, golly. Come on, guys. Don't let me get away with this. Why is what I just wrote complete and total nonsense? Well, it's not total nonsense. It's about 30% nonsense, maybe. I don't know. The curl of a vector field is a what? Is it a scalar or is it a vector?
Vector.
A vector. What am I missing?
The x hat.
Very good. The other hint here is that without the x hat sub k, there'd be a sum over k here. Okay, fine. Well, I guess I can't say that, but let me shut up. So, of course, that transfers down to here and here as well. All right. So with that, lo and behold, we have C times the curl of F plus the curl of G, right? Which implies that 1 and 2 hold, right? To get 1, we put C equals to 1. To get 2, we put the G to be 0, right? You guys can easily see that the divergence or the curl of the 0 vector field is just 0, right? All right. All right, great. How about 3? Then we're up against the curl of G times F. So same basic starting point, sum over I, J, and K, 1 to 3, epsilon I, J, K, partial x sub I of G times F sub I. Right? Now, let me save myself a little bit of writing here. What is this? This is going to give me partial G, partial x sub I times F sub I, plus G times partial F sub I, partial x sub I, right? And then, so I can rewrite this as the sum over I, J, K of epsilon I, J, K. What is partial G, partial I? That's nabla G, the ith component, right? And whoa, mind blown. Oh, I did the same stupid mistake again, didn't I? I forgot the x hat. Yeah, thank you. So that's from this term, right? And then the other one, pull the G out. We've got the sum over I, J, K of epsilon I, J, K, partial F. What? Wait, what? Whoa. Dudes. Something wrong here. Come on, what's wrong here? My eyes are getting fuzzy or something. The first I goes with the derivative. The second J goes with it's the component to which is be differentiated, which is the jth component. This is not the jth component. I've written the ith component. This I should be a j. Likewise, this should be a j, and that should be a j. Right. So all my j corrections are in blue. So we got partial fj, partial x sub I, and then of course we've still got our x hat sub k. Good news. Looks like we made it. Like this is the gradient of G cross product with the vector field F. And then here we've got the scalar function G times the curl of F. And the indices are in the right order. We didn't need the minus as it turns out. So you can erase that question mark and go, nope, it's good. It's good. Now, 4, I'm not going to subject you to the proof of that in class. I mean, I'm going to project it in a minute here, but I won't. I won't make you see that. It's bad. It's bad. So we'll come back to this. Save yourself a spot for that. But the next order of business is to talk about the higher order identities. There's 3 of these. So, and what I'm about to tell you is more important than the thing I've skipped. But the three identities that are, very, very helpful in the study of structure of vector fields. Oopsie. Are as follows. These are sort of second derivative identities that involve mixing of these vector derivatives. All right? So like the first is the divergence of the curl. What do you guys think the divergence of the curl would be? What do you guys think the curl of the gradient would be? And last but a little bit different, what do you think the curl of the curl would be? Notice that's a little bit different. I asked what the curl of the cross product was for number 4. Now I'm taking the curl of the curl. That's a little bit different, isn't it? One of these is not like the other, all right? But 2 of these have the same answer. Care to guess the answer?
Zero.
0 is a good guess. Which 2 of these are 0?
Top 2.
Top 2. Very good. And this one is not. That one, in fact, is the gradient of the divergence minus what's something known as the Laplacian of f. So that is, well, let's see how to find. This is the, well, nabla squared is this thing. So when I write nabla squared f, it's a vector of second partial derivatives. So this is proposition 7.2.5. All right. It's exactly this operator here. So like in detail, in detail, this is, it's like the first thing gives me the x derivative of that plus you take the first component, right, and calculate its second partial. Well, golly, it's Ow. Trust me, you don't want me to write this out. Same for 2 and 3 over here, but with, instead of having F1 there, you'd have F2 and F3 for the y and the z components. But it is the curl of a curl. It's a vector field. Okay, so which one do you guys want to try to show is true, 1 or 2? You guys pick. We'll do one over the other. You want to do 2? All right, 2 it is. What is the curl of the gradient? So this is the sum, I, j, k, epsilon, I, j, k, and then we do partial xi, right, of partial f, partial x sub j, times x hat sub k. since if we calculate the gradient of f, what is the jth component? Well, the jth component of the gradient is by definition partial f partial x of j. All right. Now, what do we know about mixed partial derivatives? What do we know about mixed partial derivatives? What can we do? This is partial xj, partial f partial xi, right? We can flip the I and the j there, right? What happens if I flip the I and the j over here, though? Right. But the order of summation doesn't matter, right? So what you're looking at is minus nabla across the gradient of f. Therefore, if something is minus itself, and we're not working under a weird number system, it's 0. All right? Now, I introduced a question last class, which was, is it possible for a vector field to be the gradient of another vector field, right? This identity that we've just discovered is very helpful towards that aim. Like, let's think of a hypothetical vector field, all right? And let's ask the question, can it be written as the gradient of another vector field? All right, let's think about this. Let me make up one. All right, so example 2, I guess. Suppose we're looking at f of xyz equal to x squared yz z cubed. All right? My question is this equal to nabla, let's say g, for some g? I'll use f, little f. You guys are okay. I can use a big F and a little f at the same time. I think we'll be okay. So listen, here's the deal. If f is equal to nabla f, right? Then what's the curl of f? It's the curl of the gradient of little f, right? Which has to be 0. But does the curl of this f equal to 0? Because if it doesn't, we know that the search for a little function f whose gradient is the vector field is an impossible one. So this identity that we've just derived is actually very helpful in that regard. It can show us when is it possible, right? Okay, so let's calculate the curl of this vector field. Yeah, let's do it. Now, if you guys want, let me introduce yet another. This is just a mnemonic, right? But maybe you guys like this more. And if you like it more, you can use it. I don't mind. Just use it correctly. I like the notation partial x, partial y, partial z. It's less writing, but it gets the thought across just fine, right? Now the x, we got x squared, we got yz, and we got z cubed, right? So the way this works is we do x hat times partial y, z cubed, minus partial z, yz, right? The derivative has to come first. You guys get that, right? Yeah? Okay. We don't work with derivatives that go the other way, right? In my research, I sometimes worked with derivatives that do this. I don't like those. Derivatives should work that way. So xz cubed minus partial z, oopsie, oh, x squared, yeah. Plus z hat, what we got here? Partial x yz minus partial y x squared, right? All right, so what do we get? Let me declare all the zeros. 0, 0, this is 0, big fat 0, 0. Actually, everything's 0 here except that right there, but all it takes is one thing. That is what? Minus y, yeah. So in other words, the curl is minus y, 0, 0, which tells us that no, f such that big F equals to the gradient of f does not exist. Because if it did, it would violate this identity. Right? It would force a contradiction because the curl of the gradient is 0, and yet the curl of this vector field is non-zero. Yeah? Example 3. Let's do this for like an arbitrary vector field, yeah? Let's let f equal to p, q, r. That's, you know, the usual Stewarty notation for it. Let's calculate the curl of that. What's the curl of f equal to? If we use this handy dandy, I don't know, do you guys like this more than my formula? You're allowed to like this more. I have mixed feelings, but so we have x hat times like I'm going to use the other notation if you guys don't mind. R sub y minus q sub z minus y hat times r sub x minus p sub z plus z hat qx minus py. So apparently the condition that the curl of PQR be 0 is equivalent to what? We need partial r, partial y equal to partial q, partial z. We need partial r, partial x equal to partial p, partial z. And we need partial q, partial x equal to partial p, partial y. We need all three of those at once in order for the curl to be 0. Do you guys remember the homework problem about this? But we didn't know the curl then, right? So we just had to kind of discover it through hunting. But now it's simply a consequence of this vector identity. Yeah. Curl 0 requires these conditions on the partial derivatives of the components, right? Any questions? All right, my fourth example is a physical one. By the way, the proof of number 1